Hello students, in this video we'll discuss two functions that have extreme oscillations near the origin and that causes the derivative to not exist or the derivative to exist but fail to be continuous. So let's look at two special functions. Consider first f of x is x times the sine of 1 over x, okay? Now, let's think about this function over here. So what's happening is that I claim that as x is really small, what can we notice? There's clearly potentially an issue over here when x is equal to 0. But let's compute the limit as x goes to 0. So note, the limit as x approaches 0 of this function x times sine of 1 over x. What I'll do is I'll put absolute values around everything. And now we can note that this x sine 1 over x, since sine is bigger than, no more than 1, is less than or equal to x. So this limit is controlled by absolute value x, and so this limit is equal to 0, which says that the limit in question inside the absolute values also has to be equal to 0. Okay, so now I can define the function like this. This is a valid function if x is not equal to 0, and x is not equal to 0, and then let's say it's equal to 0 when x is equal to 0. So now I have a perfectly well-defined function, and this function is continuous at x equals 0. So this function f is continuous at x equals 0. All right? But now let's look at the derivative of this function. So what's f prime going to be? So f prime of x for x not equal to 0 is going to be x times the cosine of 1 over x times negative 1 over x squared, and then just plus sine of 1 over x, okay? And so all total what we have over here is this derivative. This is of course valid when x is not equal to 0, okay? And now if x is equal to 0, what happens? That's what the derivative is when x is not equal to 0. That's perfectly well defined. However, if we try to compute f prime of 0, what would f prime of 0 have to be? It would be the limit as h goes to 0 of f of h minus f of 0 all divided by h, right? Now, of course, f of 0 is 0, so this is just the limit as h goes to 0 of h sine of 1 over h, those cancel, and then you have the limit as h goes to 0 of sine of 1 over h, and this limit does not exist, okay? Of course, the easiest way to see that is if you plug in this sequence of points, to look at the sequence of points, an. So we know that the sine of any multiple of pi over 2 is going to be either plus or minus 1, right? So if I look at those reciprocals of those things, so if we look at, for example, 2 over pi, so if h was 2 over pi, that would give me a 1 in the numerator. That would give me a sine of 1. If I went over here to, instead of 2 pi, to like a 2 over 5 pi, then the reciprocal of that would be what? The reciprocal of that would be sine of 5 pi over 2, which is also 1. Then I can do like 2 over 9 pi. And this sequence over here of values of h is tending to 0, and the value of the sine at those values of h is equal to 1. However, if I looked at the values of h, which was 2 over 3 pi, or 2 over 7 pi, or 2 over 11 pi, then this sequence is also going to 0, but now the sine at those values is negative 1, because the sine of 3 pi over 2, the sine of 7 pi over 2 are all equal to negative 1. So I think I have a, let's see, so everything works out over here well, so let's make sure I have everything right. Yes, so I have to add 2 pi to that. Good. Okay, excellent. And so now that limit does not exist. So this function is not differentiable at 0. So this function is continuous at x equals 0, but not differentiable. F is not differentiable at x equals 0. Okay. Now let's do one more. Let's modify this a little bit. Let's consider this function over here, g of x. So g of x is going to be x squared times the sine of 1 over x, okay? That's, of course, what it is when x is not equal to 0, and by the same argument over here, we can see that this function g is 0, x equals 0. So here, g is continuous at x equals 0. So g is a continuous function at x equals 0. And let's compute the derivative away from 0. So what's the derivative away from 0? So the derivative away from 0, so g prime of x, if x is not equal to 0, is going to be x squared times the cosine of 1 over x times negative 1 over x squared, okay? And then over here, then I have a what? Then I have a plus 2x, and then the sine of 1 over x. So that's the derivative if x is not equal to 0. Now notice over here, what does this term simplify to? This just simplifies to negative cosine of 1 over x, okay? And by a similar reasoning to above over here, as x goes to 0, this limit will not exist. But let's compute g prime of 0. What's g prime of 0? It's the limit, as h goes to 0, of g of h minus g of 0, all divided by h. And so now, of course, what happens? So now I can use this formula. That's going to be an h squared sine of 1 over h. So this is exactly equal to the limit, as h goes to 0, of h squared sine of 1 over h over h. One of the h's cancels, and now I just have h times the sine of 1 over h, and that limit is equal to 0. So this function is continuous at x equals 0, and g is differentiable at 0. So g is differentiable at 0, not g prime. G differentiable at x equals 0. But g prime is not continuous at 0, is not continuous at x equals 0, because this limit over here does not exist as x tends to 0. So while g is differentiable at 0, the derivative is not continuous at that point. So this gives us a good sort of collection of examples to think about when we're talking about the relationships between continuity, differentiability, and continuity of the derivative. Thank you very much.